Okay. Um, right, guys. Let's start with this week's contents. So previously, we learned something which is known as heat transfer from extended surfaces, which more popularly we call it as fins. And if we do a quick recap on like what we did, uh, basically we saw what is the governing equation that determines how the temperature distribution in those extended surfaces would look like. We basically solved an ODE, which looks basically like this. It's a second order homogeneous ODE. Of course, it's linear. And then what we did is we came out with an expression for at least the case when the tip was insulated. The rate of heat transfer was given by square root of EHK AC theta B times the tan hyperbolic of M multiplied by L, where this M is a fin parameter, which is basically the square root of pH by KAC, where P is the perimeter of the fin, H was the heat transfer coefficient of the ambient fluid, and K happens to be the thermal conductivity, with AC being the cross-sectional area. So we looked into two of the most important parameters, which basically governs how effect, I mean, how like so I would say how effective the use of fin is, and typically it is also given by the fin effectiveness, which basically is the ratio of the rate of heat transfer from the fin to the rate of heat transfer when there was no fin. We looked into something which is also known as the fin efficiency, which is basically the rate of heat transfer from the fin to the maximum rate of heat transfer that would take place when the entire fin is maintained as the base temperature. So this is something that we looked at, and also we saw that for the use of fin to be beneficial, uh, our effectiveness has to be greater than one. Okay, but in the meantime, you should also appreciate that although your effectiveness can be greater than one, your efficiency, which is basically the rate of heat transfer from the fin to the rate of heat transfer when the entire fin is at the base temperature, this cannot be greater than one. Okay, so your effectiveness of the fin has to be greater than one, but your efficiency is always less than one. So you can keep that in mind. And by efficiency, I mean the fin efficiency. Okay, then we solved a couple of problems associated with fins. And also, what we did is we also looked something which is known as the overall fin efficiency. So we said that it is customary to determine the overall fin efficiency of a fin structure when we have a fin array instead of using a single fin, which is basically more seen in practical applications like that of a bike engines or that of or fin structure in transformers and so on and so forth. Okay, so when we have so the idea is that when we have multiple fins, okay, that are spaced equally, okay, and then we have a bare area which we denoted is by AB. The temperature of this bare area we denoted it by theta B. The idea is that we represented the overall efficiency of this fin array structure. So the idea is that we represented the efficiency of this fin array structure by something which is known as the overall fin efficiency, which says that is the rate of heat transfer from this entire area to the maximum rate of heat transfer, just like the definition of a single fin efficiency that we determined. Okay. The only difference here lies in the fact that this QT now is basically the total heat rate from the surface area AP, and this AP covered the fin areas and the exposed areas. Okay. So this is something known as the overall fin efficiency. This is something that we have a looked upon, and this is where we stopped in the last class. Okay. So we had couple of breaks, but now we are all set to like begin week 6. Okay, so what we will do today is, but before that, like if you have any questions on the on the assignments or on the topics up to week 5, you can just let me know through the chat or post it in the discussion forum. Okay. Uh, if you have any questions, always feel free to interrupt, as I said. But today, what we are going to do is in this week, we will see something which is associated with the week 6 of your lecture classes, and the assignment that I think that you already submitted in week 6, but nevertheless today we will discuss discuss the part of week 6 that we missed it in the previous week. And as I said, there will also be a class tomorrow, which is basically the readjustment of the class that we missed on the 31st of August. And on tomorrow's class, we will start off with the contents of week 7, which is basically transient heat transfer. But today we will see the contents of week 6. Let's proceed systematically, and we will. So in that we will study something which is known as 2D heat transfer, and I think this was associated. This is also associated with the contents of the lecture series on week 6. Okay. So this is something that we plan to do today. And as I said, there will also be a class tomorrow. Okay. And this is the adjustment of the class that was missed on 31st August. And tomorrow we will start off with the agenda for week 7, and that is the transient heat transfer, and we will see something which is known as the lump capacitance model and heat transfer in a semi-infinite solid and so on and so forth. Okay. So that is something that we will see tomorrow. But yeah, today we will be sticking ourselves, as I said, to 2D heat transfer, and in that we will be discussing. So this 2D heat transfer is so we may not encounter much problems in this 2D heat transfer. Keeping in mind that we will be solving a few of the problems involving something which is known as the safe factor, and I think you also had problems in your assignments associated with this safe factor. But these problems are relatively simple, and we will see that. But apart from this, we don't have much of the problems to be solved in this 2D heat transfer, but there are some understanding that that are left to be built. So we will. So apart from this, apart from solving problems associated with this safe factor, we will see one of the most important technique, and you guys have already had a glimpse of that in your lecture classes, is something known as the separation of variable. And this is something that even till now, most people use to get exact solutions of the so-called Laplace equation, which is basically the heat diffusion equation in 2D. Okay. And having said that, although we'll be seeing, so basically you have learned this technique in your lecture classes, so we'll not go much deep into it. We will do, so what we will do is we will solve a sum associated with the separation of variables. And in that, we will try to understand how this separation of variable technique works, what's the governing equation in case of a 2D heat transfer, and things like that. Okay. And but having said that, although I said this separation of variables is a much involved and a much useful technique, there are still certain limitations on this separation of variable technique. Okay. And these limitations you will see. So these limitations can be overcome by using something which is known as method of superposition, solely because, as we will see later, that the governing equations are linear and homogeneous. Okay. Yeah, I mean, what I mean to say is that since the governing equations are linear, we can convert a non-homogeneous equation into a homogeneous equation by using certain transformation, so that we can use separation of variables. And that procedure of doing that is something which is known as method of superposition, as we will see later on. So this is the agenda, a broad agenda of what we are going to do today. So we'll begin by understanding something which is known as method of separation of variables. This is exactly similar. The method is exactly similar to the one that we have already seen in the theory class of week 6. Nevertheless, we will solve a sum and try to get further more insights on this method, which is known as the method of separation of variables. The second task is that we will see something which is known as conduction safe factor associated with 2D heat transfer, which is basically this. This is rather very simple, yet we will be solving certain problems which are similar to the ones that are given in your assignment associated with this conduction heat transfer. And finally, we will wrap up by learning something which is known as method of superposition. Okay, so before beginning, I'll wait for a couple of minutes. If you have any doubts associated with this or anything that you might encounter it up till till the previous assignment, you can basically let me know. I'll stop here for a couple of minutes, and then we will start off with the discussion on this method of separation of variables. In the meantime, if you have any doubts, you can just let me know. You may type in the chat box, or as I always say, if you have doubts later on, you can always post it in the discussion forum of the group. Okay. All right. So if you don't have any doubts, so we will start off with something which is known as 2D heat transfer. So the very first thing is, right? So the very first thing that comes to our mind when I say we are going to do a 2D heat transfer analysis is that earlier when the temperature profile was just a function of x, and we say this to be a 1D heat transfer problem. Okay. So we commonly say this as a 1D heat transfer problem. Now my temperature will be a function of two variables, and if at all I say it's a steady state problem, then my temperature field will be a function of two spatial variables, let's say x and y, and that's why it makes the problem a two-dimensional in nature, because your temperature essentially varies on x and it also varies along y. Okay, and that's why it becomes a 2D heat transfer problem. And if we deal with a 2D heat transfer problem, keeping in mind that we do not have a heat generation, okay, we do not have a heat generation in our system, and also our problem is of steady state, then the heat diffusion equation that we have already seen for a 1D case now transforms into a 2D case as follows. So the heat diffusion equation can now be written as, so if we use a 2D, so if we are in this 2D domain, our heat diffusion equation basically becomes something like this: del square T by del x square plus del square T by del y square, and this is equals to 0. That is typically because we are assuming that there is no heat generation. Let's say let's say my boundary is just a slab. Okay, let's say my boundary is just a slab. I fix my axis in this way such that this becomes my x-axis and this becomes my y-axis. And let's say I prescribe some temperature. Let's say this temperature is T0, this is T0, this is T0, and this is T1. And let's say my T1 is greater than T0. In that context, if I want to derive what is the temperature profile in for this slab, okay, for this slab, keeping in mind that I have all the Dirichlet condition. Dirichlet condition means that I have directly specified the value of the unknown variable on the boundaries. That condition is typically known as the Dirichlet condition. So if I have the Dirichlet condition on its four boundaries, then if I want to basically get the temperature profile, I need to solve this heat diffusion equation, which is now in 2D. That is typically because now my domain is no longer one-dimensional, and my temperature distribution will now be a function of both x and y. Okay, so for that, I need to solve this two-dimensional heat equation. And by the way, this form of this heat equation, that is a 2D heat equation without any heat generation and in steady state, this has got a spatial name. So can you tell me what is the spatial name of these kind of equations? Del square T by del. So can you tell me what is the spatial name? What kind of these equations are generally known as? Or what is this form of this equation generally known as? Can you tell me? What is the name of these kind of equations? Yeah, it is differential equation. True. That is yeah. To be precise, these are partial differential equation, but in the literature, it has got a special name. Okay. These kind of equations are known as Laplace equation. So did you heard the name of this? These kind of equations are known as Laplace equations. So did you heard so did you hear this name before? Yes, exactly. So this is called Laplace equation. This equation is called Laplace equation because you can write this equation. So this equation can be simplified as something like this: del square T, okay, is basically equal to 0, where this del square is known as the Laplacian operator. Okay, this del square is known as your Laplacian operator. What do you write for it? Okay. Okay. Now it is important to basically note that this Laplace equation. So remember, this del square is okay. This del square is basically known as your Laplacian operator, and in 2D space, the Laplacian operator basically looks at something like this, as you were already seen from the equation. If it's a 3D space, we'll have del square T or dou square by dou z square. Okay, in 3D space. But since we are in 2D space, the Laplacian equator basically looks something like this. Now, the important characteristics of a Laplacian equation is this. Can you tell me, is this equation homogeneous or non-homogeneous? Can you tell me? Is it a homogeneous equation or a non-homogeneous equation? So the question is that the equation that I wrote here, yes, it's a homogeneous. So that is correct. It's a homogeneous equation. But the best way of checking, that is for all the viewers who are just viewing this video, the best way of checking whether an equation is homogeneous or non-homogeneous is that if I put t equal to 0 in this solution, I end up getting the left-hand side to be equal to the right-hand side, which means t equal to 0 is a trivial solution of this partial differential equation or of this Laplace equation. And if there exists a trivial solution, okay, then such kind of equations are known as homogeneous equation. Okay, so these are the characteristics of a Laplace equation so that it is homogeneous. Okay. Now, can you tell me, is this equation linear or non-linear? Two things you need to tell me. Is this equation linear and what is the order of this equation? Is this a linear equation or is this a non-linear equation? Yes? Can you give it a try? Okay, so I'll give you a hint. Yes, linear second order, exactly. So this is a linear, that is exactly. This is a linear and it's a second order equation. So again, the best way of checking whether an equation is linear or non-linear is to see that is my dependent variable multiplied with itself or with its derivative uh, in the equation or not. Basically, what I mean to say is that if I have a term, let's say t times del t by del x, or if I have a term like t square, or let's say if I have a term like del t by del x into del t by del x, then all these terms, if so it happens to be in my equation, this brings nonlinearity into our problem. But in any of the terms in this Laplace equation, I do not have the dependent variable multiplied with itself, or the dependent variable derivatives are multiplied with each other, and so on and so forth. All the combinations that I basically showed here. So if such combination does not exist, then my equation is a linear equation. Now, and of course, it's a second order because the highest power of the derivative is 2 here. Okay. So I say this typically because if I have an equation which is homogeneous, okay, if I have an equation which is homogeneous and if it is linear, then I mean, a way to solve these kind of equations is the method of separation of variable. But I would say it is not always a universal way to solve these kind of equations, because although, as you have seen in your problem, although you can have a governing equation which is homogeneous and of course it's linear, if your boundary conditions are not homogeneous, then at least in one of the direction, then you cannot use method of separation of variables. I repeat, if I have an equation which is homogeneous, okay, and of course it's linear, then I said that you can use method of separation of variable, but this is not universally true, because if I have my boundary conditions which are non-homogeneous in at least one direction, or sorry, if I have my boundary conditions which are non-homogeneous in two of the directions, let's say in x and y, then you cannot basically apply method of separation of variables, and for that you need to use something which is known as transformation. Okay, so this is the, like, I would say it is the, like, what do you say, like, it's a drawback of the method of separation of variable, but this is how exactly it goes. There are several other methods, like you say, by using finite difference method. This is one way of computing the equations which do not fall into the category of solving it by method of separation of variables. Also, there is something which is known as method of superposition, and we will see so. So with this background, uh, again, I'll stop here for some time, but with this background, let's proceed with solving a simple question associated with this method of separation of variables. But before that, like, I'll stop here for some time. I hope this is clear what basically is a Laplace equation. Okay, what so so method of separation of variable is one of the techniques of solving a Laplace equation, provided you have a homogeneous governing equation, you have a linear governing equation, which we have, and also in one of the direction your boundary conditions need to be homogeneous. Okay, if that is satisfied, it is the perfect recipe for solving a PDE using a method of separation of variables. Okay. All right, guys. So if you have any questions, you can ask, or else we will solve a problem which is associated with this method of separation of variables. Okay. So let's have a quick look at this problem. It says that we have a two-dimensional rectangular plate, okay, just like the one that I showed, that is subjected to the boundary condition as shown below. So it starts off with a simple boundary condition. So it's a Dirichlet boundary condition on the four edges. And as I said, if the unknown variable is directly prescribed on the boundary, okay, then the boundary condition is known as the Dirichlet boundary condition. Can you tell me, if I have, instead of like prescribing the temperature here, if I prescribe, like, let's say del T by del X on this face, can you tell me what is the boundary condition called? Or in other words, I put it more simpler way, or in other words, instead of like prescribing directly the unknown variable, say the temperature on its face, or on this boundary, if I say that the boundary condition on this face is not now the temperature, but the derivative of the temperature, okay, as some value, okay, then can you tell me what is this kind of boundary conditions called? So like just how the earlier boundary condition, when I just specified the temperature, is known as Dirichlet boundary condition. The boundary conditions where I now prescribe the derivative of the dependent variable, these are known as Neumann boundary condition. You should remember the name. These are known as Neumann boundary condition. So Neumann conditions means you are prescribing uh, the derivative of the dependent variable at the boundaries. Okay. But luckily for this problem, we do not have a Neumann boundary condition, because we just have this temperature. We just have this temperature that is defined on this face. So this, without any doubt, this is a Dirichlet condition. As I have said, this is a Dirichlet boundary condition. But frequently, you may also encounter the other boundary condition, which is known as a Neumann boundary condition. This is also one of your problems in the assignment that I think you have solved. Okay, I mean, one of the questions, that's a theory questions in your assignment. Okay, but nevertheless, our task is now to solve this. So the basically what we need to do is, in this two-dimensional domain, we just need to evaluate the temperature distribution. So let's begin. So as usual, the governing equations for this case from the heat diffusion equation turns out to be the Laplace equation, as we have already seen, basically because this is a 2D problem without heat generation, and it's a steady state problem that we are dealing with. And in the Cartesian coordinate, this Laplacian del square turns out to be del square T by del x2 plus del square T by del y2 equals to 0. So this is the governing equation that we are going to solve, and it is subjected. So it's not just the governing equation that we can solve and just get the answer. We must also systematically write the boundary condition, right? So let's write the boundary condition first. So yes, steady state boundary conditions are also known as Dirichlet boundary condition. Not really, Sandvi. That is typically because in this problem also, let's say, so this is a steady state problem, right? So what I can do is, instead of defining defining temperature here as T to be equal to A times X, I can also define on this face that the del T by del X, right? And this would be just A. Okay. So what I'm saying is, instead of defining this T equal to AX, what I can do is, on this face I can also determine del T by del X, which is basically equal to A. These two conditions are exactly the same. This is basically equivalent to this. Okay. Then this condition happens to be a Neumann boundary condition, but this is also a steady state problem, right? So it is not necessary that your problem needs to be a steady state in order to have a Dirichlet boundary condition. An unsteady problem can also have a Dirichlet boundary condition. The sole method of whether observing whether it's a Dirichlet boundary condition or it's a Neumann boundary condition is to see that if directly the dependent variable is specified on the boundary, then it's a Dirichlet boundary condition. If the derivative of the dependent variable is specified on the boundary, it's a Neumann boundary condition. Okay, so I hope this is clear, right? I hope it's clear. And by the way, I forgot to mention one thing. So yes, okay, thank you. Thank you for the question. By the way, I forgot to mention one thing. So in some cases, you may also encounter boundary conditions which have a both Dirichlet and a Neumann boundary condition involved together. And such kind of boundary conditions are known as mixed boundary condition. For instance, I'll just give you an example. Let's say I have a temperature that is prescribed on this plate, which is basically equal to T equal to A times X. And I can also have a temperature that is prescribed on this plate, and this time I say it's del T by del X is equal to some B. Then, as you can see, I have a Dirichlet boundary condition on this space as this, and on this space I have a Neumann boundary condition. Then, in this problem, the overall boundary conditions that we have, they are so it's a mixture of a Dirichlet boundary condition on one face and a Neumann boundary condition on the other face. And such kind of boundary conditions are known as mixed boundary condition, or sometimes they are known as Robin boundary condition. Okay. So I hope this is clear. So, so yeah, that is just about the boundary condition. But anyway, so now since our problem is much more simplified, we just have a Dirichlet boundary condition on the four faces. Our task is basically to write down the the boundary conditions now. So can you tell me one thing, that how many boundary conditions do we need to basically solve this problem, to basically close this problem? Can you tell me? So just by looking at this, don't look into the picture. That of course you can tell the answer from there. But fundamentally, if I ask you that I give you a partial differential equation of this form, okay, which is basically a PDE and it's second order, it's a PDE in X and Y, then can you tell me, in order to like have a full form solution of this PDE, how many boundary conditions do we require? Yes, a try. It's 4, right? Because it's very simple. So forget about these terms, okay? Then this equation is just an ODE. And then we solve multiple equations involving, let's say, d2t by dx2 equal to 0. If you remember, this was basically the 1D heat equation without heat generation. And we say that the temperature profile was linear and so on and so forth. Okay. In those examples, we have two boundary conditions, typically because this t was now just a function of x and it was second order in x. And that was an ODE. Now our domain has expanded from a 1D domain to a 2D domain, which means now I require 4 boundary conditions in order to close this problem, because I have a second order PDE in X and I have a second order PDE in Y. Okay, I mean in a PDE I have this second order term in X and a second order term in Y, and that's why typically this problem has 4 boundary conditions being prescribed on these 4 boundaries. Okay, I hope this is clear. So now let's write down the boundary conditions. So for this phase, what we have? So for this phase, I have temperature. So let's write down the boundary conditions. Okay. So for this phase, what do we have? So we have temperature uh, at for all x at y equal to 0 is basically equal to 0. This is one boundary condition. The second boundary condition we can write on this phase, okay, which is your temperature for all x at y equal to b is equal to some constant a times x. Okay. The third boundary condition is for these phases and these phases. Okay. So you can write this, the temperature at x equal to 0 for all y is basically equals to 0, and your temperature at x equal to where? At x equal to, for this phase it is at x equal to a. Your temperature at x equal to a for all y is basically equals to 0. So these are the 4 boundary conditions that we have in order to like have a closed form solution of the PDE, of this Laplacian PDE that we need to solve. Okay. So let's name this as, so how do we name it? Let's name it as equation 1a. Maybe this is 1b, this is 1c, and 1d. All right. So now, as I have said that we will use something which is known as the method of separation of variable. This is possible because, as you can see, at least in one direction, your boundary conditions are also homogeneous. For instance, if I just pick the x direction, let's say this direction, on this face, the boundary condition is homogeneous, meaning that your temperature is 0 there. And on this face also, the boundary condition is homogeneous. And if there exists at least one face where the boundary condition is homogeneous, your governing equation is also homogeneous, and it's, of course, it's linear, then it's the perfect recipe for applying the method of separation of variable. And since we are lucky in this case that our boundary condition is homogeneous, at least in the x direction, we will apply something which is known as the method of separation of variable. Okay. Now, the natural question arises that what happens if I don't have a homogeneous boundary condition on x as well? Let's say I prescribe this temperature as some b times y. Okay. Then can we apply method of separation of variable or not? That's the question. And the natural answer, okay, to this question is that you cannot directly apply the method of separation of variable. Okay, what you can do is there is something which is known as principle of superposition, as we will see later on, is that we will like decompose this problem into two simpler problems, okay, by using something which is known as superposition. And then what we will do is we'll collect the answer from the one problem and then the other problem, and then we'll add the answer from these two problems to get the total solution. Okay, and this is possible. This decomposition into two simpler problem is possible because our governing equation is linear in nature. Okay, so long as you don't have a non-linear governing equation, you can always use the method of superposition. Okay, so these are some basic stuffs that is associated with the method of variable separation and the limitations that is associated with the method of variable separation. Okay, so but for this problem and for the problem that mostly we will see in this course, okay, we will encounter homogeneous boundary condition at least in one direction. Okay, all right. So any questions? Okay, if no questions, we will begin by, we have stated the governing equation, we have stated the four boundary condition. The next task is to use the method of separation of variables to basically solve this. And as the name suggests, the method. So the first step, okay, for using the method of separation of variable is we will take. We'll assume that the temperature which we are going to solve, okay, the temperature field. So you can appreciate that the unknown is basically a temperature field, right? We need to solve the temperature field subjected to these four boundary conditions. Okay. So what we will do is we will assume that your temperature field is basically some function of x multiplied by some function of y. And the the as the name suggests, the separation of variable is basically what we have done. Okay, we have separated the temperature variable as a multiplication of a single variable in x and a single variable in y. Okay, and this is the first step of the method of separation of variable. Okay, then the second step is basically what we will do is we will substitute this. So let's say we name this as 2a. The second step is that, see, we have decomposed this temperature variable as some g of x multiplied by some f of y. So now instead of the temperature being an unknown, we have basically segregated it into two variables, g of x and f of y. So the next step naturally is that we need to look for equations which will govern how g of x varies and f of y vary. Okay, I hope that is clear. And for that, what we will do is we will substitute this equation 2a in this governing equation, which is 1. And this is exactly the procedure that is followed in the theory classes. That's why we will not go into the much details of this, because I mean you have already seen that in the theory classes. So this is just the practice of we are doing by using the method of separation of variables. Okay. So when we substitute this 2a, that is this form of the temperature distribution, into this equation 1, it basically comes out as what? So your del square t by del x2, this becomes as f of y times d2g by dx2, and your del square t by del I2 basically becomes g times d2f by dy2. Okay, all you need to do is just substitute this form of your temperature into the governing equation. Now if you just substitute this, what we will end up is we will end up getting, so our equation was what? Our equation was del square t by del x2 plus del square t by del y2 equals to 0. And then if we substitute these forms, okay, what we will get is we will get f times d2g by tx2 plus g times t2f by dy2, and this is equals to 0. Okay, and here we will do a trick. What we will do is we'll divide the entire equation. So what we'll do is we'll divide the equation by f times g, by f of y times g of x. Okay, and if we do this division, it is very easy. We can see that this will become 1 by g times of d2g by dx2. Okay, and this would become 1 plus 1 by f times d2f by d dy2, and this is equal to 0. Okay, so now what we'll do is we'll do a small trick. We will put this 1 by f times d2f by dy2 on one side, and we'll take this 1 by g times d2g by dx2 on the other side. And you can do the vice versa. You can take the f to the other side and g to the this side. This will basically remain the same. Okay, so now you need to tell me what is so special about this form of the like simplified OD. I would say the simplified PDE that we get from here. Can you tell me what is so special about this form of the PDE? So we didn't do anything, right? So what we did is we just assumed they formed the temperature, substituted this form the temperature into the governing equation, and then did some like simple algebra to come out to this form of the like governing equation. So now can you tell me what is so special about this form of the this particular form of the governing equation? Special, I means what is the characteristic of this form of the governing equation? Yes, partial differential equation convert into two ODs. Actually, we have not yet converted into two ODs, but your idea of like your direction of thinking is correct. We have not actually converted this into two ODs, although our objective is to convert the PD into two ODs, but still we have not done the conversion yet. The characteristic or the like, I would say the what to say, the peculiarity of this form of this governing equation is that, as you can observe, this function, this 1 by f times d2f by dy square, it is just a function of y. Okay, it is just a function of y. While the other function minus 1 by g d2g by dx2, this is just a function of x. So then it becomes interesting, right? So what we are doing is we are saying that a function which is just a function of y is equal to a function which is just a function of x. Now that seems impossible, right? Because how can a function of y be equal to a function of x? But in only one special case, this is possible. And can you tell me what is that special case? Now, this is something that you need to think about. So the question is, so you can observe, like, because we have separated this t xy into some function of x times function of y, and then by doing some like simple algebraic manipulation, we say that a function of y, because this is of course a function of y, right? 1 by f times d2f by dy2. This is just some, let's say, phi of y. Okay, and this term is just some, let's say, lambda of x. And then what we are doing is we are just saying that this phi of y is basically equal to this lambda of x. Now, how can this be possible? And if at all, if it is possible, when is this possible? Can you tell me? The simple question is, when is this equality possible? So, can you give it a try, or I'll tell the answer? So the answer is that you can think about it. The answer is that this is both sides equal to the same constant. Exactly. So this is only possible. You have pinpointedly mentioned the correct answer. So the answer is that this is only possible. Okay, a function of y will be equal to a function of x, and this will be only possible. This is only possible when this is equal to some constant, and this constant we will denote it as some lambda square. Okay, now why you are using lambda square and not just some let's say lambda cube or lambda to the power 4? This is a trial and error basis. Okay, so this lambda is actually known as the eigenvalue. Okay, now why we're choosing the square of the eigenvalue is that if you let's say choose lambda to the power 3 and solve this problem, you will see that you will not get the correct answer. And that's why, like from experience and from a trial and error basis, you can prove that only lambda to the power 2 gives us an ideal solution to this basically to this form of the governing equation. Okay, so that's why we will use lambda square. Okay, so as you have correctly mentioned, that this equality is only possible when it is basically equal to some constant, and this constant will denote it as some lambda square. So in the hindsight and in the background, like knowingly or unknowingly, what we have done is we have converted these PDEs into two simple ODEs. Okay, and that is the true objective of the the method of separation of variable. Its objective is basically to convert the PDE into two different ODEs and then to solve for these two ODEs simultaneously. Okay, so this means this has to be equal to this constant in one sense, and this also has to be equal to this constant. So that's what we are going to do. So this 1 by f times d2f by dy2. Okay, this will basically be equal to what? This will basically be equal to lambda square. All right, and this now can be simplified as d2f by dy2 minus lambda square f. Okay, and f is of course a function of y, and this is equal to 0. All right, so this is the simplified ODE, one of the simplified ODE that we have extracted from the PDEs. Okay, and let's say we name this as what? Maybe we name this as equation maybe 3a. Similarly, if you find out the other ODEs in terms of g of x, it will look like this. It will look basically 1 by g times d2g by dx2, and this is equal to lambda square, which means this can be written as d2g by dx2 plus lambda square g of x equal to 0. And we name this as 3b. Okay, now the solutions of these ODEs, these are rather simple, right? Because we know, we know how to solve the solution of an ODE, which is second order, as you can see from this. It's second order, of course, it's linear and it's homogeneous. Okay, so can you tell me what is the solution of these two ODEs? Can you tell me first what is the solution of this? What is g of x? Now, this is something that you need to tell me, right? We have done this multiple times. Can you tell me what is g of x? I mean, this is a basic or else like this. So this is something that you learn in your like first year mathematics course when you study ODE. So it's a second order ODE. It's homogeneous. It's linear. So what would be g of x? Can you tell me? So just check it out. I mean, I will not go into the details of this. This. I believe you have done this multiple times. I'll just tell you the methodology. The objective is that you need to assume g of x as some e power, let's say some mx, and then substitute this into this equation to get the roots of this what we call the characteristic equation. Okay, and since it's second order, we'll have two roots for this characteristic equation, and these roots are then linearly like superimposed to get the entire solution. Okay, so this is, I believe you have already went through it, so we'll not do this in detail, but the solution of g of x now, so it can be written as some, let's say c1. So this would be cos lambda x plus c2 sine lambda x. So do you have any like problem of understanding how this solution came? So if you can't understand, let's like if you are facing a problem in understanding this, I will show you how this solution came. Okay, so you got this right? How this so you understand right how this solution came? Yes. Okay. Okay. Thank you very much. Okay. Similarly, if we solve this, maybe I'll write this now as what? Maybe I'll write this now as 3, or I'll write this now as 4a. Okay. And similarly, if you solve this equation just by the methodology that I just stated, you will simply get f of y as some, let's say, c3 e power lambda x plus c4 e power, sorry, this would be y. Okay, sorry, because your f of y is just a function of y. Basically, you are just solving this ODE. That's it. So it is c3 e power lambda y plus c4 e power minus lambda y. Okay. So we name this as 4b. All right. But we are not still done yet, right? Because yes, we know that the total solution is going to be just the product of g of x times f of y. But what we have seen is in like in kind of like bifurcating the single PD into 2 ODs, we end up getting these 4 constants, okay? C1, C2, C3, and C4. And can you tell me there is one more unknowns, okay, that is yet to be determined? Can you tell me, apart from this C1, C2, C3, and C4, there is one more unknown that unknowingly we have added in our problem. I mean, knowingly or unknowingly we have added in our problem, and that is yet to be determined. Can you tell me just by looking at these solutions? So straight away it appears that your C1, C2, C3, and C4 are unknown. Yes, lambda, exactly. So this is the, I would say this is the perfect, so this is how an eigenvalue problem actually proceeds. Okay. So since we are introducing the constant lambda square, which is basically the eigenvalue of our problem, our another task is to basically find out the eigenvalue, okay, from the like boundary condition which we already have. Okay, and this is something that we will do. So what now we will do is we will now write the boundary condition which were in terms of temperature into the forms of G and F. Okay, so let's say if we see the first boundary condition, let's say we see this boundary condition, I mean, let's say we see these two boundary conditions. Okay, so I have, so what do I have? Or let's say, okay, let's say we use these two boundary conditions first, because we, let's say first we solve this equation and then we'll go to this equation. Okay, so the third and fourth boundary condition is what? So I have this t at x equal to 0 for all y is 0, and t at x equal to a for all y is 0. Okay, so if I use this, okay, so I have what? I have t at x equal to 0 for all y is 0, and I know that my t is basically the product of g and f, and that's why I can write this as g at x equal to 0 multiplied by f of y equal to 0. Now, here is the thing. F of y cannot be equal to 0. Okay, this cannot be equal to 0, because if this becomes equals to 0, okay, then this means that this will be 0, and that's why your temperature will also be 0, and that's the trivial solution, right? But we are not interested in the trivial solution. We are looking for some specific solution involving the specific values of this lambda. Okay, and that's why this f of y cannot be equal to 0, since f of y cannot be equal to 0. That's why g at x equal to 0 will be equal to 0. And this is your transform boundary condition in x that we have obtained from the temperature boundary condition that we already have. And maybe we'll name this as what? We have named this as 4a, so we'll name it as, let's say, 4a star. Okay. Similarly, uh, the other boundary condition is t at x equal to what? At x equal to a, I think. Okay, for all y is basically equals to 0, and using the same analogy I can write it as g at x equal to a times f of y equal to 0, and simply because of the fact that f of y cannot be equal to 0, I can write it as g at x equal to a equals to 0, and this boundary condition I'll name it as 4a star star. Okay, now let's use these two boundary conditions. Let's use these and these boundary conditions into this this solution. So from the first, I would say from the first boundary condition, this 4a star star, or let's say 4a star, I have what? I have g at x equal to 0 equal to 0, which means if I just use this, I simply get C1. Yes. Okay. So if I just use this, I simply get C1 to be equal to 0. Okay. So from 4a star, I just get C1 to be equal to 0. This is simple, right? Because what I have is I have this g at x equal to, I have this g at x equal to 0, and this is basically equal to 0. And if I substitute this at x equal to 0, this becomes equal to 0, and this is 0, which just ends up. So we just end up getting C1 to be equal to 0. Okay. This is one concept by using one of the boundary conditions. Okay. If I use the second boundary condition, this is basically this, that g at x equal to a is 0. And if I substitute it here, what I will end up is, see, C1 is already 0, so we'll not bother about this term. What I will get is, I will get C2 sine, and then this is what? C2 sine lambda a is basically equal to 0. Now here is the thing. Can C2 be equal to 0? Or I would say which of these two terms, C2 and sine lambda and y, which of these can be equal to 0 and which can't be equal to 0? Can you tell me? And if C2 cannot be equal to 0, what is the reason why C2 cannot be equal to 0? Can you think about this? Like, why is this possible? Yes, can you give it a try? Like, why C2 cannot be equal to 0? See, it's very simple. If I say, see, so this says that the product of C2 times lambda a is basically equal to 0. This means I have two possibilities. Either C2 can be equal to 0, or sine lambda a can be equal to 0, or both these can be equal to 0. Now, we'll discard that both of these cannot be equal to 0. This means either this can be equal to 0 or this can be equal to 0. Now, if it happens that C2 is equal to 0, okay, and we already know that C1 is already equal to 0, which means my C1 and C2 will now both be equal to 0. And if this C1 and C2 now becomes both equals to 0, this means that my g of x will turn out to be equal to 0. And if my g of x turn out to be equal to 0, and since the temperature is just the multiplication of g times f, and if this goes out to be equal to 0, this means your temperature will also go out to be equal to 0. And similarly, we end up getting the same old trivial solution that we got. But again, I said we are not interested in the trivial solution, right? So that's why your C2 cannot be equals to 0. Okay. C2 cannot be equals to 0, which means this sine lambda a now is equal to 0. And we all know this, that if sine nx is equal to 0, that means your lambda a has to be equal to n pi. Okay. And then your lambda should be equal to n pi by a, where this n goes from 1, 2, 3 up to, like, how much number you want to find out, up to infinity. Now, an important conclusion here is that is n cannot be equal to negative. Of course, n cannot be equal to 0, because if n is 0, then again we end up getting the same trivial solution. But this n cannot be equal to negative, because you can prove that if you take the value of n to be equal to negative, this will render the fact that your lambda square will now become negative. Okay. And then again, you will not get the solution that you seek for by using the method of separation of variable. Or, like, in simple terms, just choose n to be equal to -1, and then if you substitute it and then see the final answer of the problem, you will see that n equal to -1 does not satisfy the boundary conditions, and the entire solution will just not work. Okay. And that's why this n has to be equal to a positive number. It starts from 1 and it goes till infinity. Okay. All right. So in doing so, what we found out is we have figured out what the eigenvalue, that is lambda, of our problem would basically turn out. Okay. So this we will now imitate like this. So this means by using the two boundary conditions, we have now figured out this g of x. So g of x is now basically so this g of x. So this C1 was equal to 0. C2 we have not yet determined, but we will see that's very, like, intelligently we will we do not actually need to separately determine C2, okay, and that we will see shortly. But anyways, we have determined this g of x as some C2 uh, C2 times sine of lambda x, where this lambda is basically equal to n by a, and this n takes the value of 1 to up to infinity. Okay, so any questions? We'll just name it as maybe what? Maybe we'll name it as equation 5a. All right, I'll stop here for some time. This is little bit laborious to solve, but it, as you see, it gives us many insights into when we actually solve an eigenvalue problem. Okay. All right. Is it clear? Can you tell me with an yes or no? Is it clear up to this point? Do I need to explain it again up to this point, or like is it fine? Let's check the chats. Okay. Okay. I hope it is clear. Please stop me at any point of time when you feel like you need to understand it again. But I hope this is clear now. So what we did is we have kind of figured out, not completely, although we have figured out what is basically this g of x. Okay. Now what we need to do is we'll solve it for the f of x. Okay. So f of x, we already know that the form of f of x is okay. So okay. So why will f of y will not be equal to I was not able. Okay, so there is a question why f of y will not be equal to 0. Okay, I'll explain this. Okay. All right. So I'll explain this to you why this is not possible. So why f of y cannot be equal to 0. So see. So it's basically where it's basically here. Okay. So from this boundary condition, that is from the first boundary condition, if we use the method of variable separation, we end up getting basically this. Now let's consider the other way around where f of y is basically equal to 0. Okay. Now if f of y is 0, okay, if my f of y is 0, let's say I write here. So if my f of y is 0, this means my temperature, which is basically Txy, is the product of g of x times f of y. And I say my f of y is basically equal to 0, which means that my temperature, this is 0, which means my T of x now becomes automatically b equals to 0 because f of y is 0, right? But if I say my temperature is 0, that's not the solution that I was looking, right? Because see, there is a temperature provided here, and I say that apart from a temperature that is being provided on the face, I say that my temperature field here is 0. But that is not possible, right? There has to be a non-zero temperature field that is embedded into this block simply because there will be heat transfer by conduction. Okay, and that means that T xy equals to 0 is not a physical possible solution of this eigenvalue problem, and that's why f of y cannot be equal to 0 if we want to find non-trivial solution for our problem. Did you understand that? Okay, yeah, okay, thank you very much. All right, and that is typically the reason why f of y cannot be equals to 0. Okay. All right. So now what we will do is we will we'll basically apply the boundary condition for this. We'll apply the boundary conditions here. So let's write the boundary condition. So what I have is I have my, so the third, so the third boundary condition is that I have, okay, I have what? So let's see the boundary conditions. So we have used these two boundary conditions. We are yet to use these two boundary conditions. So this is basically, so the first boundary condition is your T at x for y equal to 0 is equal to 0. And my temperature is basically the product of g of x times f at y equals to 0. And this is equals to 0. Okay. Which means again, the same logic is that g of x cannot be equals to 0. That is simply because if g of x is 0, your temperature field basically vanishes to 0, which is not physically possible. Okay. Which means that your f of y is equals to 0. F of y at y equal to 0 is 0. That is simply because since g of x is non-zero. And then if I use this, if I use this, if I use this boundary conditions into my equation, what? Oh, if I use this into my equation 4b, what do I get? I get C3 plus C4. If I use this into 4b, I get C3 plus C4 to be equals to 0. That is simple, right? Because you just need to substitute y equal to 0 here. Then this becomes C3 plus C4 is equals to 0. And then this is basically you will get C3 to be equal to minus C4. Okay. All right. So if C3 becomes equal to minus C4, then from this equation, that is from equation 4b, I can eliminate one of these C3 and C4, and I can simply kind of write it as like this. I can simply write it as f of y. I'll keep C3 there. Okay. I'll keep C3 there, and C4 I'll just write it as minus C3. So this becomes C3 times e power lambda y. C4 is minus C3, so it becomes C3 times e power minus lambda. It's just that I have just used this boundary condition. I've used this boundary condition into equation 4b. That's it. And now what I will do is I can like nicely take C3 common out of here. So this becomes C3 into e power lambda y minus e power minus lambda y. Okay. And this, at least for now, is my solution. Although in terms of C3, we have not yet determined C3, and we will see how basically we'll determine C3. But at least for this, I can name this as maybe equation 5b. Okay. All right. Any doubts till this point? I'll stop here for some time. And remember, lambda we have already determined. Your lambda is basically n pi by a. That we have already determined. Okay. All right. If no doubts, let's now do one thing. Let's now check what will be my t of xy, because we know that, because ultimately we don't need this g of x and f of y, right? We are just using this to basically solve the ODs, and after this we must like combine this g of x multiplied by f of y, because we are interested in the more physical quantity, which is the temperature field, right? So your t of xy now becomes g of x multiplied by f of y, and we have systematically determined g of x. So your g of x is basically C2 times sine lambda x. Okay, so your g of x is C2 times sine lambda x, and f of y is basically C3 times this quantity. So this is C3 times e power lambda y minus e power minus lambda y. Okay, and we'll do we'll do one more thing here. So I think you guys know that sine hyperbolic, let's say lambda y, this can be written as e power lambda y minus e power minus lambda y by 2, which means I can write e power lambda y minus e power minus lambda y equal to 2 times of sine hyperbolic lambda y. Okay, this is just to make our like solution a little bit more compact. Okay. So what we will do is, instead of this e power lambda y minus e power minus lambda y, we will replace it as 2 times of sine hyperbolic lambda y. We'll just use this in here. This means your t x comma y will basically be equal to C2 sine lambda x times C3 into 2 times sine hyperbolic lambda y. Okay. Now here we'll do something. So can I club these, these constants into just a single constant? We can do that, right? Because these are just some arbitrary constant that we have determined as a part of the integration as a part of the integration basically that we did. Okay. So, I mean, as a part of the solution of the ODEs, we have just determined this C2 and C3. So without the loss of generality, I can simply write this 2 times of, maybe I'll do one more step. I'll just write it as 2 times of C2, C3 times sine lambda x times sine hyperbolic lambda y. And what I said is that I can simply write these 2 times of C2, C3 as just some, let's say I'll write it as some, maybe what? Maybe I'll write it as, what can, I'll just write it as some phi times some phi. Okay. But this I can do, right? Can you just tell me if it is possible or not? Because see, this C2 and C3, these are some arbitrary, yes, because this C2 and C3, these are some arbitrary constant, right? So without some loss of generality, I can just replace this constant as some another constant, which is phi. Okay. So I hope you can appreciate that very cunningly. We have reduced these two constants into just one constant simply because these constants are just an arbitrary constant that we have introduced as a part of solving the ODEs. Okay. So now this temperature T of x comma y, this can be written as some phi times sine lambda x times sine lambda y. Okay. But we know that this lambda is basically equal to n pi by a, which means I can now write this equation. I can now write this equation in a more general form as, so tell me if I can write this as something like this or not. In a more general form, we can simply write it as T x comma y is equal to summation from n equal to 1 to infinity pi n times sine lambda nx times sine, this is hyperbolic, this is sine hyperbolic lambda ny. Can I write this or no? So can I just write this? See, of course we can, right? That is simply because these lambdas should be satisfied for each and every values of n, because I said that this n will vary from 1 to up to infinity, right? This means this equation should be satisfied for each and every values of n. And that means if it is satisfied for each values of n, the entire solution has to be satisfied for all the values of n. Yes, exactly. This is basically superposition. Okay. That is simply because like if it gets satisfied for one value of n, it has to be satisfied for all the other values of n, simply because all the solutions comprising of each values of n are linearly independent to the other. And that's why we can use something which is known as the method of superposition to write this as a summation form. And that's why this temperature now can be written as a summation from n equal to 1 to infinity some phi n times sine lambda nx times sine hyperbolic lambda ny, where this lambda n's, as I have already said, this lambda n's is basically equal to n pi by a. And as you have rightly pointed out, this is just superposition. You know why we are able to use this superposition? This is because the sine functions and the sine hyperbolic functions, these are orthogonal functions, which means that the solution, let's say for n equal to 2, is not dependent on the solution for n equal to 3. And such forms of these functions are known as orthogonal functions. Okay. And that's why this superposition is possible when we have these kind of orthogonal forms of the functions. Okay. We are almost there, but can you tell me, we still have to find out something. So what is left? So what is still left to be found out? Can you tell me? There is still an unknown in this solution that is yet to be found out, and we still have one boundary condition which we have not used yet. So what is still left to be found out from this solution? See, this lambda n is known. That is all know. That is, we have already found out that is lambda is basically n pi by n. But we don't know what is this phi n, right? We still need to find out this phi n, right? So this phi n is, so we'll obtain this from the one boundary condition which we have not used. So remember, we have used all the three boundary conditions, but we have not used the prescribed temperature boundary conditions on the top face. Okay, and this we will use now to basically calculate what is the value of phi n. Okay. All right. So the last step is basically to calculate the phi n. So to calculate phi n, okay, And for that, we will use the fact that my temperature at for all x at y equal to what? At y equal to b is basically equal to some constant times ax. Okay. And then what we'll do is we'll just substitute these boundary condition into basically this equation, which means I have what? I have this a times x, and this is equal to summation n equal to 1 to infinity. Okay. Phi n sine lambda nx times sine hyperbolic lambda and y is basically equal to b, so this becomes b4. All right. So now tell me, if you like, if you paid some attention, like if you like, know something which is known as the orthogonality of orthogonal functions, or there is something which is known as like, what do you say? Yeah, it's called it's called orthogonality principle basically. So using this orthogonality principle, can you now tell me how can we like evaluate this phi n? Because this phi n still needs to be evaluated, right? We don't know what is this phi n. This a times x is known. This is given to our problem. All these things are known, but we are still left to be, we are still, yet to be like, we still need to need to calculate this phi n. So what we will do is we will use something which is known as the orthogonality principle of sine and cos. Okay. So remember, these sine functions are orthogonal, which means if I if I integrate a sine function, let's say I integrate this sine, let's say mx and some sine nx, where this n and m are integers, and if I integrate this, can you tell me under what condition this integration becomes 0, and under what condition this integration does not become equals to 0, is not equal to 0? Let's say I keep it simple. I integrate this from 0 to, let's say, L. Can you tell me when does this integration becomes equals to 0? Okay, so I'll tell you. So this integration is equal to 0 when this m becomes not equals to n. Yes, exactly. When m becomes not equal to n, that's the right answer. So this integration becomes equal to 0, and this is non-zero. Okay, and when m is equal to n, this is non-zero, and its value is basically equal to L by 2 when m is equals to n. Okay, and this is basically this principle that we have used here. This principle, okay, this principle that we have used here, this is known as orthogonality principle. Okay, so now what we'll do is we will use this orthogonality principle into this into evaluating this phi n. Okay, so what I will do is, let's say I name this as some equation. Let's name these equations. There are a lot of equations now. So this is 5a. Maybe we'll name this as some 6. Okay, and maybe we'll name this as some 7. Okay, so in equation 7, what I will do is, in equation 7, I will first multiply this entire. Okay, so what I will do is we'll do a simple step. We will write this lambda n's. So we know what's lambda n, right? Lambda n is basically n pi by a. So what I will do is I will just write this lambda n as simple n pi by a. Just substitute its value. That's what we are doing. Okay, so we'll just write this as n pi by a. Okay, so now what we'll do is in equation 7 we will multiply by m pi by a, where m is just where this m is basically just what do you say? It's just an integer. First, we'll multiply by m pi by a on both sides and integrate, such that we can use the orthogonality principle that we just now saw. Okay, so if we do that, we can just basically write this as ax times sine m pi by a and we are integrating it. So this becomes an integration from 0 to, so this becomes an integration from what? We'll integrate it from 0 to a, because this integration is along x. This will be from 0 to a. Okay. And similarly on the right hand side, this becomes, so on the right hand side, instead of, so now you know that there is this summation sign, so I will not repeatedly write this summation sign. Whenever there is this phi n times this n and all this n occurring, remember that there is always a summation sign in this in the form that we are using. Okay, so I'll just remove this summation sign because it just looks too much complicated. So it becomes phi n times sine n pi by a x. Okay, and this becomes sine hyperbolic n pi a by b. And remember, we are multiplying this with sine m pi. Remember, we are multiplying this with sine m pi x by a. This becomes m pi x by a. And also we are integrating this with respect to dx. Okay, so if I just write this on more systematic way, this is nothing but integral 0 to a ax times sine m pi x by a dx, and this is nothing but integration from 0 to a phi n times of sine n pi x by a, okay, multiplied by sine hyperbolic n pi b by a multiplied by sine m pi x by a dx. All right. Now, although it looks a little bit like little bit voluminous, but we can like simplify a lot of things here. See, this phi m and this sine hyperbolic n pi b by a, these are not function of x. Okay, these are just not function of x, which means I can simply take these things to be outside the integral, and then I can just write it as integral 0 to a ax times sine m pi x by a dx, and this becomes phi n times sine hyperbolic n pi b by a. Okay, this is a constant, then it is multiplied by integral 0 to a, okay, sine n pi x by a into sine m pi x by a dx. All right, now you guys need to help me. Under what condition this integral will be non-zero? That you have already stated. Just have a look and tell me. Under what condition this integral will now be equal to non-zero? That you have already stated, right? So this integral is non-zero. This is non-zero only when n is basically equal to m. And for all other values of n not equal to m, this integral would just vanish. Okay? This means this equation will be non-zero only when my n is basically equal to m. And for all other cases, when my n is not equal to m, okay, this integral will just be equal to 0, and that's why this term would just go out to be equal to 0, which means without the loss of generality, I can just write this is as equation, sorry. And one more thing, can you tell me what is the value of this integral when n is basically equal to m? Okay, this would be just a by 2. I think it's just a by 2 pi. Just check it out. There should be a pi here. I think it should be a by 2. I think 2 pi by a. I think it is a pi by 2. Okay, just check it out because there is an inherent pi here. So I think this would be a pi by 2. Just check it out. Okay. Just look into the orthogonality of sine and you'll just check it out. But to my knowledge, to the best of my knowledge, this would be a pi by 2. But nevertheless, this is equal to a pi by 2 when n is equal to m, and this is, sorry, I just wrote, so this is not equal to 0 when n is equal to m. Okay, just 1 second. Just let me make this clear. So what I meant is that this should be 0 when n is not equal to m, and this would be a times a pi by 2 when this n is basically equal to m, which means I can simply write this now as, using the orthogonality principle, of course, I can write this now as integral 0 to a ax times sine my n is basically now equals to m, because for all other cases when n is not equal to m, this integral is equals to 0. It becomes ax times sine n pi x by a dx, and this just becomes to be equal to phi n times sine hyperbolic, okay, n pi b by a, and this is just equal to a pi by 2, which means indirectly we have found out what is phi n, right? Because you can just write phi n as 2 by a. I think this pi should be at the denominator. This pi should be here. This pi actually should be here. Just check it out at your end. I just forgot where exactly the pi was. Sorry for that. Anyways, this would be 2 pi by a. If I bring this to the other side, times integral 0 to a ax times sine n pi x by a dx divided by sine hyperbolic n pi b by a. Okay, and this is how you you have determined what is phi n, right? Because can you tell me the right hand side of this form is known or unknown? Can you tell me? So is this a known or an unknown quantity? Yes. Sorry. So this is a known quantity, right? That is simply because this integration, see, you are integrating this. So this is a sine function integrated along x, and a is just a constant that is given. Yeah, exactly. It's a known. So this is just an integration, and this integration is known. You can simply use integration by parts to basically calculate this integration, which means you have like uniquely determined what is phi n just by using the leftover boundary condition, that is the boundary condition on the top face, and using the orthogonality principle of the sine function. So this means you have determined phi n, and that's all is left to be determined, right? Because your temperature, if you remember, your t as a function of x or y was nothing but summation n equal to 1 to infinity. It was what? It was basically this, right? It was basically this. So the only thing that was yet to be determined is this phi n, and that is something that we have determined. So it is 1 to infinity. It was phi n times sine lambda nx. Your lambda n is basically n pi a by x sine hyperbolic. It was the sine hyperbolic what? The sine hyperbolic lambda n y. So it becomes sine hyperbolic lambda n was n pi a times y. Okay, so that's the solution, and this phi n's is basically equal to this. Okay, so in a way you have uniquely determined the solution, the entire solution. So where I just write it, okay, where your phi n is basically equal to 2 pi by a, which is basically this. Okay, it's 2 pi by a, and this is your integral 0 to a ax. Okay, this is small a. So for the confusion, it's small a. Okay, this ax times sine n pi x by a dx divided by sine hyperbolic n pi b by a. Okay, so this phi n is uniquely determined using this, and substitute phi n to uniquely basically get your temperature as a function of x and y. That's the entire solution of this problem. Okay. All right. So what I will do is I'll stop here for some time. I understand it's a bit long. So I want you guys to basically see the steps that we have done. I hope you are taking notes with me as long as so when I'm writing, I hope you are just taking notes. I see to basically I want you to basically go through the procedures that we have did. The procedures are simple. It's just that the algebra is little bit involved here. But yes, we have uniquely determined this form of the temperature distribution that we will get. Okay. Remember, this sine hyperbolic n pi b by a, this is just a constant. Okay. There is no dependency of y here. Or the only dependency arises is basically this term sine n pi by a into y. Okay. So the idea is that all I'm saying is that this phi n is basically a constant. It is not a function of x and y, because there is no y dependency here, and the x dependency is basically removed by this integration. If you do this integration, I have not done it here. At your home, you can just try out this integration, use integration by parts. If you do this integration, you will just end up getting a number here. Okay, which means your phi n's are just a number, and of course they are obviously dependent on the integer value of n. Okay, that's what the idea is. So I'll stop here for some time. We will do one more thing quickly. And so the algebra of this, what we call this variable separation, is so big that people do not use this in practical like scenarios. And for that, we will see something, an alternative and a much easier technique, which is known as the method of like using shape factors. Okay, but before that, I'll stop here for some time. I'll come back in just 1 minute. In the meantime, you can just have a look at your notes, and if at all at any point of the analysis you have any doubt, like you tell me, and I'll be happy to explain. So I'll just come in 1 minute. Okay. All right, guys. So any doubts on this? I understand big uh, this is a big calculation, and yes, I agree that the method of separation of variables, although like like it is it is still used by many, like in many ways, but it is little bit involved. And also there are a lot of assumptions. For instance, the boundary condition need to be homogeneous, your governing equation has to be homogeneous and linear, and because of all this, in practical applications, people don't use, although in theory and in research, people use the solution of variable separation to basically solve PDE. It is not just confined to the heat equation. Okay, you can just solve any Laplace equation using this method of separation of variables. Okay, for instance, this transient heat diffusion equation, okay, transient 1D heat diffusion equation can also be solved using the method of separation of variable. Okay, but nevertheless, people use this in research, but in practical application, because of its cumbersomeness, as you have seen, the algebra that it involves, and although like its assumptions and limitation, like makes it little bit less convenience to use it in practical senses. And that's why like there is another way of actually calculating 2D heat transfer is something which is known as by using shape factors. Okay. Now these shape factors, this is very easy. So how these shape factors are calculated is that for prescribed geometries, okay, the value of shape factor, that is the expression of shape factor, as you have seen in your like theory class, this is already known. For instance, let's say I have a sphere that is inside my earth crust. Okay, then if I know the diameter of this sphere, okay, and if I know the distance up to which uh, this depth is like so if I know the depth up to which the sphere is being immersed inside the earth surface, or let's say in inside any surface, and if I know the temperature of this sphere on its surface as T1, and if I know the temperature of this surface on the earth surface, let's say as T2, then you can very nicely write down the expression of the rate of heat transfer from this sphere to basically the earth surface and up to this surface as a shape factor multiplied by the thermal conductivity of the medium here, which is K, and the temperature difference delta T from 1 to 2, which means I can simply write it as Q dot as some shape factor times K times T1 minus T2. And let's say I can simplify this Q dot as T1 minus T2 by 1 by Sk. This means, I hope you have seen this. I'll not explain this much because it is already explained like thoroughly in the theory classes, the use of shape factor. But like we will try to solve a couple of problems. These are very easy problems. But the the idea is that now I can represent this 1 by Sk in terms of a resistance. This I write it as RTH. Okay. And then this resistance using the shape factor analysis basically becomes equal to 1 by the shape factor multiplied by the K, which is your thermal conductivity. Now, the whole idea is basically finding out the expression of S. Now, I think in your theory classes, you have already seen that this expression of S depends on the geometry. That like if there is a sphere that is being submerged in a semi-infinite solid, then this expression for S, if you remember, this expression for S, this basically comes out to be 1 second. So this expression for S basically comes out to be something like this. It is 2 pi times the diameter by 1 by d by 4z. So this is what the expression of S looks like. For this particular, remember, this is for this particular configuration. Whenever there is a sphere that is being submerged in a semi-infinite domain, which is basically this domain. Okay. So now it's very simple, right? So if you know the temperature of this surface and if you know the temperature on this surface, okay, and you know the diameter and the depth of immersion, you can basically calculate the rate of heat transfer. Okay, without like going into the this method of separation of variables, solving the 2D problem and so on and so forth. Okay, now you cannot, in fact, you cannot use method of separation of variable here. Okay, because this is a much more a complicated problem, and that's why people have used this shape factor analysis. Now, if you ask me how this expression of shape factor come, this basically can, so you need to go from the first principle to basically come into these expressions for these shape factors. Okay, I hope this is clear on how basically you need to you basically find out the shape factors. Any questions on this? So we'll solve one question from the assignment just to make you clear on how to basically deal with problems on shape factor. So what we will do is, so in your assignment, this is just your assignment problem. I hope you have done it. If not, like we will solve this. So what they have said is there is a cylinder which is immersed into the earth surface up to a distance z. That is the central distance from this cylinder to the surface of the earth is denoted by z. The diameter of the cylinder is of course d. The surface temperature of the cylinder is given as T1, while the surface temperature on the earth surface is given as T2. Okay, and based on this, what they have asked is what is the rate of heat loss from this cylinder to the ambient, that is to the ambient solid, semi-infinite solid here. Okay, and then this can be easily solved by using the shape factor analysis. Okay, because if you look into the textbook of Incropera, I have taken this from the textbook of Incropera, it says that your shape factor, if my length is very much larger than d, and if let's say my z is greater than 3d by 2, your shape factor will be basically 2 pi l by ln of 4z by d. And here, indeed, you can find out that your 3 times 3 times d by 2 basically becomes equal to what? It becomes 1.5 times of 0.6, which is what? Which is equal to 0.9. Okay. This means indeed, in your case, your Z, which is the depth of immersion, which is 1.8, is of course greater than 3 times d by 2. Okay. Which means, yes, indeed, your Z is greater than 3 times d by 2. So you can use this form of the shape factor now. You can use this form because consider the fact that it's already given that the length of the cylinder is much longer than its diameter, which means these two conditions are indeed satisfied, and your Z is greater than 3 times d by 2, which means your shape factor for this case, would be just 2 pi L by ln of 4Z by d, and you know all the values, right? Because Z and D are known. So this means the rate of heat transfer, now you can easily find out, you can see how much simple it is. Okay, it's just like finding the appropriate formula for the shape factor. That's it. So your rate of heat transfer now would be just the shape factor times K times the temperature difference, which is T1 minus T2. Okay. And if you substitute the value of S here, this basically becomes 2 pi L by ln of 4Z by D, okay, times the thermal conductivity times the T1 minus T2. All right. And since they're asking to find out, so they're asking basically to find out the rate of heat transfer per unit length. That's why we'll bring the length to the other side. And this becomes Q dot by L equals to 2 pi ln of 4Z by D into K into T1 minus T2. Now here everything is known. This Z is known, so we'll just substitute the values. This is basically 2 pi ln of 4 times your Z is 1.8. Your diameter is basically equal to what? 0.6. Your diameter is 0.6. Okay. This is 0.6. All right. And then thermal conductivity of the Earth's surface is given to be equal to 0.51. Okay. This is 0.51 multiplied by the T1 minus T2. Your T1 is 95 degrees Celsius. T2 is 25 degrees Celsius. So this becomes 95 minus 25. And can you tell me, just do this sum, and can you tell me what is the value of Q dot by L? Because they're asking you to calculate the rate of heat transfer per unit length of the cylinder. Okay. Can you tell me what is the value of L? I mean, this is one of your problems of your assignment. So I think you should be in a good position to do this. Can you tell me, just do the math? Just the simple math. If you have a calculator at your end, you can do this math. So I have done it. I got the answer to be around, I got the answer to be roughly around, 110.8 watt per meter. Is this the answer that you got? Like, can you confirm with an yes or no? I hope you have solved this problem in the assignment, right? Because the due date is already gone. So I think you guys have solved this problem. So it's just a representative way of just showing how easy the shape factor analysis is. You just need to know the geometry and just need to see what is the expression for shape factor of corresponding to that particular geometry. So yes, okay, very nice. Okay, all right, thank you. Okay, so this is a more practical way of basically solving a 2D problem using the shape factor. So if you look into the textbook of Incropera, into the chapter two-dimensional heat transfer, two-dimensional conduction heat transfer, and then go into the paragraph which have the shape factor, you will see that for multiple geometries, the expressions of shape factors are defined just like this. Okay, this is just for this particular geometry. Let's say for a sphere, I already said this, for a sphere, the shape factor basically looks something like this. So similarly, the shape factors are basically defined for all other geometries. Now, how they are calculated, this is beyond the scope of this subject. Okay, like it is not possible to show you how this basically comes. Okay, yes, this is analogous to resistance because you can always write your shape factor in terms of the resistance. But in 2D, instead of like defining it in terms of the resistance, you cannot define it in the resistance formulation. For instance, you cannot write this You cannot write this as ln of R2 by R1 by 2 pi k. You cannot do that because this was only applicable for a 1D case. Okay. And that's why what people do is people drew an analogous drew an analogy from a one-dimensional problem to a two-dimensional problem using this shape factor principle. And for most of the practical geometries, the expressions of shape factors are known. And from that, you can evaluate the rate of heat transfer. Okay. Now, in your exams, I understand it is not possible to remember this. So, in your exams, if there is a question on shape factor, you will be given what is the geometry and correspondingly the expression for shape factor corresponding to that geometry. Okay. All right. So, this was the solution by shape factor. Any questions on this? This was easy, right? I mean, there is nothing much to be explained. It has also been nicely explained in the lecture classes. But I understand the method of superposition was a little bit involved, but I think if you have followed the algebra, this is how it is actually done. Having said that, in most of the research and in most of the problems, people use method of superposition till now, like in most of the research problem. But in more practical problems, using that is little bit difficult and cumbersome, as you have seen. So you have solved a simple problem. Okay, this is just remember, this is just a simple problem that we solved, where the temperature was basically prescribed on one face, and in all other faces, there were just homogeneous boundary conditions. Okay, but still you can appreciate how big and how cumbersome the algebra has basically become, and that's why in practical sense it is little bit difficult to use this shape factor analysis. Okay, so we don't have much time today, so I'll stop this. I'll stop the discussion for today. I'm still left with one more thing, like there is something called method of superposition. So maybe we'll discuss that a little bit in the next class, and then we'll move into the transient heat transfer tomorrow. The next class is basically tomorrow. That's the like that's the class that we missed on the 31st of August, which we will do tomorrow. That's the idea. But we will start tomorrow's class with little bit discussion on the method of superposition, and then we'll move into something which is known as the lumped capacitance analysis, which is basically the transient heat transfer problem. But we will stop here since we do not have much time. We'll stop this here today. If you have any doubts on the discussion that we had today, mainly, so I believe safe factor is easy. I think you won't have much of a doubt there. But if you have any doubt related to the method of separation of variables and the Laplace problem, but by the way, can you tell me? I just had a quick question. Can you tell me if I if I have a 2D heat transfer problem with heat generation, then of course my governing equation would now becomes, let's say, del 2t by del x2 plus del 2t by del y2. And remember, this is also one of your assignment problem. So if I have a 2D heat transfer problem with heat generation, then this can be written as q dot by k equal to 0, where your q dot is your volumetric heat generation. Then this equation, yes, so you can basically write this as, let's say, del 2t by del x2 plus del 2t by del y2 equal to minus q dot by k. Then this equation has got a special name. Can you tell me now this is not a Laplace equation? Can you tell me why? First of all, can you tell me why this is not a Laplace equation now? What makes it different from the Laplace equation? And what is the name of this equation? This equation has also got a special name. Yeah, can you give it a try? This is the last question, and we will stop this. We'll stop the discussion by just answering this question. Can you tell me? So, can you just tell me? So, I'll just also write down the Laplace equation for the ease of your understanding. So, the Laplace equation was del square t by del x2 plus del square t by del y2 equals to 0. This was your Laplace equation. Okay. Now, how is this equation different from the Laplace equation in terms of mathematics? Of course, I understand that the right hand side of this equation is non-zero, but what is this known as in terms of mathematics of or in terms of the like in terms of the language of partial differential equation? What is this? How is this different? Can you tell me? So can you tell me, is this equation homogeneous or not? No, sir, that's why no more Laplace equation. Okay, yes, exactly, exactly. So this means the very nature of this equation, which makes it non-homogeneous, is the inclusion of this volumetric heat generation term. Which means if I put the values of t to be equal to 0, that means t equal to 0 is not a trivial solution of this. However, t equal to 0 was a trivial solution of the Laplace equation. Okay, so that's why even though this is linear, this equation is non-homogeneous. So if this is non-homogeneous, you cannot directly apply the method of separation of variable. And this equation has got a special name. Okay, this equation is known as a Poisson equation, and it is just not confined to it is just not confined to the temperature distribution only. So the canonical form of a Poisson equation is this form. It is del square, let's say, some phi equal to some source term which we write it as f. This is basically the canonical form of a Poisson equation, and this form is essentially agreed by this form of the heat diffusion equation. So this is del square, as you can see. Yes, this is del square, and the source term is basically this q dot by k. Okay, and if I have a source term, then my problem is no longer then my problem is no longer homogeneous, and I cannot simply use the method of separation of variable. Okay, and in that sense, what we will do is, in order to use method of separation of variable, we will use something which is known as superposition. So what we will do is, so what people generally do is, they take this t as a function of xy, they write this as some g of xy plus some f of x, where this f of x, I mean this heat generation, is dumped into the solution of f of x, and g of xy simply satisfies the Laplace equation. Okay, I will show you in the next class how this is basically done, and this has also been shown in the theory classes, but we will just see a gist of it. And by the way, if we use this transformation, you can simply use the Laplace equation, and I mean, you can simply solve the Laplace equation for g of xy and just solve the 1D heat generation problem for f of x, and just combine the solution of this. You know, this is possible only because even if this is non-homogeneous, this is still linear. And if your governing equation is linear, you can simply use the method of superposition. Okay, so the idea is, I mean, just don't, I mean, I'm sorry if I just make it a little bit complicated, since I'm just trying to end it. But the idea is that if you have this kind of equation and you still want to apply the method of separation of variable, you need to use something which is known as method of superposition, where you basically decompose your dependent variable into a form which is a form of x and y plus a form of x, such that this q dot by k comes into the solution of this f of x. That means this f of x would just satisfy d2f by dx2 plus q dot by k equal to 0. And this g of xy would just satisfy the Laplacian equation del square g of x equals to 0. And if I just separately find out the solution of these two problems and just add it, I simply get the solution of this t of xy. Okay, and that is the beauty and the strength of this method of superposition. And this is solely possible since the governing equations, although it is non-homogeneous, it's linear, just like the Laplace equation. Okay, so that's the broad idea. I have just given the idea. So we'll just recapitulate this in the next class, and then we'll begin with something which is known as the transient heat transfer. This is a little bit, so the next topic is a little bit relatively easy topic. There is something which is known as the lump capacity analysis, where it is basically just a formula which you need to apply. Okay, the derivation is, of course, like, I think the derivation was done in the week 7 lectures on this transient heat conduction, but we will use the formula to basically solve problems which are related to the assignment of week 7. Okay, I mean, related to the problems on this lump capacitance model. Okay, all right. So if you have any questions, you can ask me, and if not, like, we'll meet tomorrow at the same time, 3 to 5 p.m. And as I said, tomorrow's class is an extra class. From the next week onwards, we will have our usual Saturday timing, just like today, from 3 to 5. The class on tomorrow is an extra class, which was basically done for the readjustment on the missed class on the 31st of August. Okay. Uh, all right. So I think you have just got separate emails also regarding this class. So this was the idea. But anyways, like, if you have any questions, you can ask, or else, like, thank you for attending the session. Thank you, Sanvi, for being present in the session. And, like, for all other viewers, you can look into the session. This will be posted in the website, and it will also be posted in YouTube, so you can have a look. onto the videos, and hopefully like it will be helpful for you in solving the assignment. So remember, we have mostly covered all the assignment questions while we discuss this today's topic. Okay, the assignment questions are just simple questions of the discussions that we had today. Okay, and I hope this is beneficial to you. I mean, we are keeping the spirit that we have not directly solved the assignments, because that is against the spirit of the course, right? It's just that you will just copy what I have done in the solution. But the discussions, in a way, if we just discuss this, it will be easier, and also we have not directly solved the problem. Also, it will be easier for you to understand how the assignment problems are being solved. Okay. All right. So if you have any questions, you can ask, or else like we'll call it a day. Thank you very much for joining. We'll meet tomorrow at the same time from 3 to 5 p.m. Thank you very much.